2007 diode, which look like this. The diode has the cathode and the anode. So the line, this line that you can see here, it's a cathode. This should be connected to the negative side as well. And it looks exactly like the schematic that you have. So this line on the diode, the line that you would see here on the diode, indicates the line that we have on the diode here. So this should be connected. In forward bias, this indicates the negative or the cathode, and it should be connected to the negative end. We have two situations here. We have it in forward bias and in reverse bias. What we would do here is simply we would put the diode, we would connect the diode to a power supply. We would start with very low voltage. In your case, you can, if you don't have a power supply, you can start with a 1.3 AA battery, for example, then connect them in series and build a 3 volt, then a 4.5 volt, 6 volt, 7.5 volts, and a 9 volt eventually. And obviously you can start from 0 volts. But the point here is that when you start from 0 volts, I'm going to start with 0 volts and I would show you how it works. You would have obviously 0 volts in the output. But once you start increasing the voltage, something interesting happens. So you would see here, if I increase the voltage to 1 volt, 2 volts, we would see that the output voltage, the voltage of the diode would be fixed around, now I've increased it to around 10, 12 volts. You would see that the diode's voltage would not change significantly after 0.7 volts, and it will hover around 0.6 or 0.7 volts depending on the diode that you would have. This means that once the diode is in forward bias, the voltage with diode would be constantly around 0.7 volts, and it will keep it that way. But in reverse bias, this won't happen. In reverse bias, when you put it in reverse bias and you connect the cathode to the positive and the anode to the negative, when you increase the voltage, and it's above 0.7 volt, which is the forward bias voltage, the diode becomes an open circuit. And for example, if I put my voltage on 10 volts, the voltage would be fixed around 11 or 10 volts. Now it's 11 volts. So this becomes an open circuit. Since it's an open circuit, you won't have any current passing this, and this voltage would be the same as the voltage of the source. So for example, if I put this in 4.7 volts, and this would show me 4.7 volts as well. And again, you can measure the current as well. Since this is an open circuit, the current you're going to have is going to be probably around 0 milliamps. So I would disconnect this, bridge these two, and you would see that the current that I'm going to have for this particular case is 0, because this is in forward bias and you won't see any current. But in forward bias, increasing the voltage would also increase the current. Again, you have to fill the table for this one as well. And for the last problem, figure 3, we would keep this resistor. And the connection would look like this. The anode is connected to the positive, cathode is connected to the resistor. And then this resistor is connected to another resistor, which is in parallel with the diode. So these two are connected in parallel, and the diode is connected in a way which the anode is connected to R1 and the cathode is connected to the ground. So I would have a connection like this. So D1. The anode is connected to positive. The cathode is connected to to R1. And then R1 is connected to R2, which is in parallel with D2. Again, you can use 1 in 4001, 1 in 4007, 1 in 4004. Again, here we would connect it again to a 10 volt, 9 volt, and we can measure the voltage on R1, which in this case, again, I would put it in parallel with R1. And we would measure in this case, it's like around 3 volts. The voltage on this diode is exactly the same as the voltage of a forward bias diode, which is 0.6. Because it's a silicon diode, it's like around 0.6 or 0.7, depending on your diode and the power supply. And then on this diode, again, it's 0.6, again, because it's a silicon diode, it's in forward bias. But since this diode and this resistors are in parallel, they will share the same voltage. And since this voltage is 0.65, the voltage on R2 would also be 0.65 as well. If we want to measure the current again, you can take the resistor out and put it on current, bridge the gap using the multimeter, and measure the current as well. So this current is the current that's passing these two, and then you can separate these two again and measure the current passing through R2 and D2 as well. And for this case, because I have a 4.7 kilo ohm resistor, my current is around 3.3 milliamps. So today we did 2 labs, actually 3 labs from the lab manual, but when you're on write a lab report, it's going to be 2 labs. So lab report number from lab 7, part A and B, or figure 1 and 2, and then we completed lab manual parts 7.1 and 7.2, and then lab manual number 2. If you don't have an LDR, you can order one and do it next week. They are pretty cheap, by the way, and you can stop by. I can give you the LDR. If you have it in your pack, you can use it. And then part 1, 2, and 3 from lab manual number 3 as well. You don't need to do part 2 lab number 2 because we don't have a thermistor in our kits. So you just have to do part 1 and complete the lab reports and the tables for that one. I hope you'll learn from this class. Let me know if you have any questions. Just email me with any questions if you have. I'm also available on Wednesdays and Fridays. I'm here all day if you want to come to the lab, and if you have any questions, please come to my office at my office hours, or contact me via email, or just stop by on Wednesdays and Fridays. See you next week on another video on the lab manuals.